So in this video, we want to talk about partial pressures and Dalton's law. So partial pressures and Dalton's law is the pressures of a container that contains a mixture of gases. All right, so if you have multiple different types of gases mixed together within a container, this is where we use partial pressure in Dalton's law. All right, and so partial pressure, we're looking at the contribution of a given gas in a mixture to the total pressure. So if you had three different gases, all right, and within a container, how much each of those gas contribute to the total pressure is the partial pressure, each one individually, right? And so a couple of things to keep in mind. Each particle in the gas acts independently, so the chemical identity of its neighbors is irrelevant, all right? So meaning that, because if you have a container of hydrogen, oxygen, and neon, how hydrogen behaves does not change because oxygen, neon is in the same container as it. All right, that's essentially what it's saying. Mixtures of gases behave the same as pure gases and obey the same laws. So whether you have a pure substance or mixtures, if they act ideally, they all act ideally. Okay, and then pressures exerted by each gas depends on the frequency of collisions of its molecules with the walls of the containers. This frequency does not change when other gases are present. So the key point is that whether you have more different types of gases, the frequency or the pressures of these individual gases will not change because there's a new substance that's in there. Okay. Which leads us to what we call Dalton's law. And so Dalton's law basically states that the total pressure exerted by a gas is the sum of the partial pressures of the components. All right, so the individual types of gases in the mixture. So in other words, the total pressure, okay, pressure total is equal to the partial pressure of a gas 1 plus partial pressure of gas 2 plus the partial pressure of gas 3, and so on and so on. All right, so the more gases you have, the more you add on to this. Okay, so here's an example. Humid air on a warm summer day is approximately 20% oxygen, 75% nitrogen, 4% water vapor, and 1% argon. What is the partial pressure of each of the components if the atmospheric pressure is 750 millimeters of mercury? Okay, and so according to Dalton's law, all right, P total, in this case, the total pressure is by the pressure of oxygen plus the pressure of nitrogen plus the pressure of water vapor plus the pressure of argon. Okay, so we have these four different substances that contribute to, and each of its partial pressures that will contribute to the total pressure. All right, now it tells you that the total pressure is 750 millimeters mercury. So how do we go about kind of figure out what's the partial pressure of each of these components? Well, I'll tell you the percentages of each one. All right. And so because we know the percentages of each one, in relations to the total pressure, then we could use, basically just taking the total pressure and then multiplying by the decimal version of the pressure of the percentage, and we will know what's the pressure of each one. So like, for example, for oxygen, all right, we see that the partial pressure of oxygen is 20% of the total atmosphere, or 20% of the total pressure. And the total pressure is 750 millimeter mercury. All right, so if you take 20% times 750, we get that the partial pressure is 150 millimeter mercury. All right. Now for nitrogen, the partial pressure of nitrogen is roughly 75% of the total pressure, which is 750. So if we put that, we multiply those two numbers, we get 560 millimeter mercury. All right. The partial pressure for water vapor, it says that about you got 4% of the atmosphere is water vapor, multiplied by the total pressure, and if you do this, you get about 30 millimeter mercury. And then last but not least, for argon, the partial pressure of argon is 1% times 750 mmHg, and you put that in the calculator, you get 8 mmHg. So here are your partial pressures for each one, and if you add them up, you get roughly the total partial pressure of if you add them up, you get the total pressure, not total partial pressure, but the total pressure of the atmosphere itself. Okay.